Okay, so maybe why don't we start 5 minutes earlier? I guess others can come in. So welcome to the machine learning class. We're going to have lectures on Mondays from 11 to 2, probably from 11 to 1:30. And also we'll probably be taking a break. So after an hour and a half, you'll have a 10-15-minute break so that you can just, otherwise it's pretty hard to sit in the class for 3 hours. It's even harder for you than for me. Just for people who are taking the class, you're welcome to audit the class, obviously, but for people who are taking the class, here's how the evaluation is going to be working. There'll be 2 assignments. Each assignment is going to be worth 20%. And then we're going to have individual projects. Okay? And the projects are going to be 60% for the course. We're going to have project proposals, 10%. Then we're going to have oral presentations, so we'll dedicate one class to having maybe 5-10-minute presentations for the project that you're going to be working on. And then obviously there's going to be project write-up. Okay? And that's going to be 40% of the course, of the grade. Now, check the website for the updates. These are just tentative dates when the assignments are going to be out and when the project proposal is going to be due. So roughly speaking, in mid-February, you should have your project proposal, so you should have a pretty good idea of what you want to be working on. And obviously, I'll give you more details about what I'm expecting from the project and how it's going to be structured. Okay? And by the way, when I go through the class, if you have any questions, feel free to ask me. Or if I start talking very softly, sort of yell so that I can talk louder. Okay? Okay, so what's the idea behind projects? So this is an advanced class, and the idea behind the final project is to basically give you a little bit of an experience to do some research. You want to do an original piece of research in machine learning, and then writing up your results in a coherent fashion. Okay? So what is expected from the project is fairly simple. Original idea, you can describe it, you can relate it to other methods, you implement and test it on some real-world problem. A lot of times when people took this class before, if you're coming from different areas, you might think about what you're working on during your PhD studies, and maybe you can pick something that's relevant. So what you expected to do, you'll need to write some basic code, run it on some data, make some figures, read a few background papers, and collect references, as well as writing up. Typically, people write up about 8 pages of the project. And again, I'll give you some, for people who are actually going to be taking this class for credit, I'll give you some ideas of what kind of projects you might be working on and such. Okay? And this is something for people who are taking the class just to keep in mind as we go through the course. Okay, textbooks. Right. There are a few textbooks, good ones. There is a book by Chris Bishop on pattern recognition and machine learning. So that's primarily the book that I'm going to be following. Okay? And at the end of every lecture on Monday, I will give you, the chapters that you need to read and such. So that's a book that you probably want to have if you're taking this class for credit. There's also a good book by Kevin Murphy. And again, some of the things that I'm going to be talking about are going to be covered in Kevin's book here. There's also a good book by Hasty, Tixerani, and Friedman, The Elements of Statistical Learning. This book is actually available online for free, so you can just download it. And also a book by David Mackay on information theory, inference, and learning algorithms. And again, this book is also available online for free. Okay. So the first 2 books, you have to buy them. They are quite expensive, I think. The second 2 books are basically available online for free. Okay. Okay, so what is machine learning? So the way I'm going to be structuring the course is that today's lecture is going to be more of an introduction lecture. So for many of you, particularly for people coming from statistics background, a lot of the things that I'm going to be talking about today is probably just basic review. Machine learning is a very dynamic field, right? And it lies at the intersection of statistics and computer science. Typically, people in machine learning, they're saving in statistics as well as in computer science. And the goal of machine learning, statistical machine learning, is to develop algorithms that can learn from data by constructing probabilistic models and stochastic models that can be used for making predictions. Okay? And let me give you some examples of what I mean. There's been a lot of successes in machine learning. If you look at biostatistics, computational biology, a lot of people are using machine learning methods in that field. If you look at neuroscience or medical imaging is another big growing field that makes use of statistical machine learning. If you look at more applied fields like information retrieval or natural language processing, I'm going to show you some examples of that, such as dealing with text, audio, image retrieval, or text analysis and such. Speech recognition is another big area. If any of you are using Google Phone, the speech recognition system was basically built based on the research that was developed here in Toronto, which is quite exciting. Robotics. If you've heard about autonomous car driving, right, so that's using machine learning. A lot of these different areas are using machine learning. And what's been happening in the last few years is that we've been having a huge increase in computational power, as well as the amount of the data that's available to us. Right? So that's been a very big drive for a lot of recent successes. You know, if you look at images, if you look at text, if you look at relational data, and facial and such, if you look at scientific data, one of the things that we're trying to do in that field is how can we develop models, statistical models that can discover structure, cause, or statistical correlations from the data. Okay? And a lot of what we're going to be covering in this class is going to be, by the way, you guys can just come in and there are a few spots here and here. Okay, a lot of what we're going to be covering in this class will be dealing with how we can construct these kinds of models. Okay? Let me give you one example. This is the model that we'll probably be looking at the second half of the course, but this is one particular example to just give you. This is a model called Boltzmann machine, sometimes also called Markov-random fields. It's a class of ungraphical models. But imagine you have a model. You have some input data. So input data could represent pixel intensities of an image, words from web pages, or speech signal, whatever your data is. And you might have some target variables, a response. So for example, some class labels or categories or phonemes if you want to do speech recognition. So you're trying to model the joint distribution between targets and the input data. You have some model parameters. Obviously, a lot of models that we're going to be looking at will have model parameters. And you also have something that's called latent variables or hidden variables. So what can we do here? Here's one example, one application of this model. You take a web page, and you represent the data in terms of bag of words representation. So you just have a vector that counts how many times you observe a particular word that's happening on the web page. And these latent variables here represent hidden topics. You can think of them as latent topics, or something that tells us about correlation structure between words that you see in the web page, on the web page. Right? If you look at this latent structure and you visualize it in a two-dimensional space, this is how it looks like. Right? This is an instance of unsupervised learning. So just look at the collection of web pages. And by extracting certain correlation structure between words, you can lay them out, all of these web pages, in a 2D plot. It's kind of interesting. It sort of finds these topics, these latent topics that is discussed. A lot of documents about accounts are sitting here, energy markets are sitting here and such. how many of you have heard about PCA, Principal Component Analysis? All right, that's good. So you can view this model as a form of nonlinear extension of PCA. Here's another model. It's been very popular in the recommendation system domain. So companies like Netflix, for example, are using these models to recommend you movies. Right? And this is just another model. It's an instance of a different model, something that's called hierarchical Bayesian model. And the goal here is to try to complete the entries, the missing entries in the matrix. So think about this particular graph here. You have users, and you have movies, or you have songs. Right? And each user provides a few ratings. Right? So the user number one, basically, didn't really like the first song, and kind of like doesn't like any of the song. Right? And the goal is, by looking at the structure, you want to extract the preferences, user preferences. So you can recommend the items to users. So effectively, you want to complete these missing entries of the matrix. And one particular model, again, we're going to cover this model, I think, in the second half of the class, is the hierarchical Bayesian model. So here you're basically saying that you want to model the ratings, the observed ratings. You have some latent variables. You have some latent user feature vectors, latent item feature vectors. And you're modeling them through a specific way. Again, the semantics or the details of this model, it's not important that you understand them now. I'm just showing you some examples. We can put something that's called prio over these latent variables. And again, the idea here is that we're trying to infer some preferences of users from that data. And then we can make a prediction. One interesting thing about making predictions, and again, I'm going to look at the second half of the class, is we're going to have to deal with integrals. Okay? Typically, we're going to have to deal with high-dimensional integrals. This is something that's called predictive distribution. The space, we're going to be integrating always very high-dimensional, so we have to somehow deal with these integrals, and one way of dealing with them would be to use techniques like Markov chain Monte Carlo methods that we'll cover in this class. And again, if you look at the kind of structure that the model is discovering in the Netflix data, is an example of Netflix data sets. So how many of you have heard about Netflix Prize data set? Well, Netflix Prize. Back in 2006, 2007, Netflix basically released a data set, and they said whoever can improve our base system by 10%, we'll give them $1 million. Right? So a lot of people were trying to improve the base system by 10%. The funny story about Netflix is that initially they were thinking about whether they would give $1 million to somebody who can improve the system by 5%. And then they decided to go for 10%, which was a very good decision because within the first 2 weeks, people improved the system by 5%. So the value of crowdsourcing. A lot of smart people out there. Yeah.
The speaker at the opening conference next week won the prize.
Oh.
He's speaking on Monday morning, a week from today.
Oh, so that's that. Yeah, that's great. So there is a. Yeah, I should also point out there is a few workshops that are going to be taking place at the fields during this term, and a lot of fantastic speakers are going to be giving talks. So I encourage you to sort of attend some of the talks if you can. So what are we going to be covering in this class? We're going to look at the linear methods for regression classification, just to set things up, so that notation-wise and everything, which will set up the baseline. We're going to look at model assessment, model selection. We're going to look at graphical models, Bayesian maps, Markov random fields, and Michelin random fields. And then in the second half of the course, we're going to look at approximate inference. So we're going to look at variational inference in particular, mean field approximations and such. We're going to look at the basic sampling algorithms, including Markov chain Monte Carlo, deep sampling, and Metropolis-Hastings. We're also going to look at mixture models and generalized mixture models. And a lot of emphasis is also going to be placed on unsupervised learning, such as probabilistic PCA and factor analysis. And then we're also going to focus on some of the more advanced techniques. Those would be Gaussian processes using for regression and classification, and also we're going to be looking at deep learning models. As we go through the course, I'll introduce those models. Okay? So that's a tentative list of things that we're going to cover. So let me just give you a little indications on the types of learning. Okay? Suppose you're observing a series of input vectors, x1 up to x2, 3, 4, and such. There are different kinds of learning paradigms. One of them, which is pretty popular, is supervised learning. Okay? And the idea of supervised learning is that in addition to the input, you have some targets, have some labels or responses. Okay? And your goal is to predict the correct output given a new input. Okay? It's a very well set up problem. So for example, for speech recognition, given a sound, you want to predict the phoneme so you can predict words and put things together. Right? Image recognition is another big area. Given an image, you want to recognize what's going on or what object is present in the image. I'm going to show you some examples of that framework. The second type of paradigm is unsupervised learning. Okay. And the idea here is that you want to build statistical models of X, or statistical model of X, which can be used for making predictions. Okay. So this is an example of, like I've shown you before, let's say you have a collection of web pages, but nobody actually gives you labels, labels the topics and such. You just want to extract some structure from the data. So things like clustering, for example, is pretty popular technique. There's also another paradigm called reinforcement learning. Right? And reinforcement learning is actually a paradigm that came from computer science. Typically unsupervised and supervised learning, a lot of these paradigms are coming from statistics and statistical physics. Reinforcement learning is something that really came from people who were working with robots and robotics. The idea here is that you have an agent, the agent produces a set of actions that affect the state of the world, and the agent receives some rewards, and the goal is to learn actions or policies that maximize the reward. The idea here is you're building a robot and you want the robot to walk through that door, then you want to give rewards to the robot and define a certain set of actions and such. This is not, we're not going to be covering this in this course. It's a separate type of, we can actually teach the whole course on that topic. And then there's also a class of fairly interesting kinds of models that are called semi-supervised. Right? The idea here is becoming increasingly popular in the machine learning community. The idea here is that we're given only a limited amount of labels, okay? But lots of unlabeled data. Right? So imagine that you can download lots of images from the web, but maybe you might only have a few labels for those images. A lot of this is being inspired by how humans are learning. Right? So the idea here is that when the kid grows up, you show your kid the laptop, and you say, that's a laptop, and basically that's it. The kid knows that this is a laptop. Right? You don't need to provide lots of different labeled examples of images of a laptop. Okay? So this is an increasingly popular framework. But let me show you one example of supervised learning. This example here. Let's see if that actually works. Here's an example of a supervised learning. Let's say I upload this image, right, and I want to ask the system to recognize what's going on in the image. Okay, this is what the system says. It says 99% it's a mosque, and then there's a dome, palace, church. Okay, so this is an example of supervised learning algorithm. Or if I upload a different image, this guy here sort of says this amphibian vehicle. That looks like an amphibian vehicle, right? Or thinks it's a lawnmower. We can sort of test the system. This is these kind of systems that are very popular right now in the computer vision communities. You can play with the system. Pick any object you want. Let's do that before we actually start doing the real stuff. Anything. Pick an object.
Let's try with the laptop.
Laptop? Okay. Let's try laptop. So I'm going to go to Google Images, right? And let's see if I I can get a laptop. These are all sort of nice looking images of laptops. Let's pick a weird one. I think that laptops are too easy. And they're too easy to classify.
How about a couch?
Couch, all right. Let's do the couch. So here's an example that you can pick a couch. Couch are pretty nice looking couches as well. How about this one? How about this one? So let's see if it allows me to. View it. All right. Okay. Good. So I'm going to take the URL and classify. Studio couch. So there you go. This is a studio couch. It's a day bed. No, it's 6% wall. Kind of looks like that. But remember, it's only 6%, right? So it really thinks it's a couch. There are also other interesting things you can go beyond just sort of classifying. You can also try to generate things. Like for example, here's an example of if you upload. This is sort of going, if you upload an image like this, right, you can build a system that actually generates sentences or descriptions of images in natural language. So here's, for example, it says, a woman has many bananas and other fruit at her stand. But these are actually generated. So this is the more actually generating sentences in the actual language. A woman dressed in bunches of bananas, and a woman's gold is being sold with bunches of bananas. Obviously, you can see that it doesn't perfect. But a woman standing next to large fruit with bananas, a woman wearing colorful bunches of bananas. Right? So it sort of gets the idea that it's a woman with bunch of bananas. Right? Or there's another example. Again, these are the systems that take the image. You have a supervised learning technique, so you learn some representation of those images. So for this thing, this is what it generates. A man wearing a helmet riding a bike racing trees. A man wearing a red jacket riding a motorcycle through the woods. A man riding a bike through the forest. A man on a bike riding on a dirt road. Right? So this is a system that basically looks at the image, tries to understand what's going on in the image, and then generates sentences in natural language. There's been a lot of excitement.
How difficult would it be to go back from the sentence, from all those random time-generated sentences back to a closest picture?
You can. So the system here is built both ways. If you give me a sentence, you can retrieve similar images, or images that are consistent with that description of the sentence. Yes. It's just that it's much nicer to go from here to here because these are sentences. These are not sentences that you retrieve from somewhere, but these are truly generated sentences. By generated, I mean that there's no sentence like this in the training set. And I'm gonna again at the second half of the class, I may mention how we build these models. Okay. Okay, supervised learning. I think that the first third of the class, we're going to look at supervised learning algorithms. Classification is the big one. Just like I showed you now, you have target outputs that are discrete class labels, and the goal is to correctly classify new inputs. So you try to separate implemented classes. Regression is another type of supervised learning algorithm, supervised learning problem, where your target outputs are continuous. And the goal is to predict, again, a target output given a new input. So you're fitting some form of regression here. Here's one example. This is one example of classification that people worked on for a very long time. This is an example of handwritten digits, and you're trying to classify each image into one of the classes. So here's an example where the system correctly classifies these images of twos. And here's where it classifies these images as images of tubes. Right. But actually, these are images of 7. So you can see that it's not very trivial to classify these things. And everything else is classified correctly. Now, in unsupervised learning, here the goal is to construct models, that expect some structure from the data. Clustering is a big one, and we're going to look at mixture models as well in this course. Trying to identify clusters in the data. Dimensionality reduction is another big area. Some form of taking high-dimensional data, compressing it down to low-dimensional space so you can visualize it. Trying to model the data density, or finding hidden causes from the data, and what these models can be used for: structure discovery, anomaly detection is another big area, trying to identify something that doesn't fit in with your data. Data compression, data visualization, and sometimes these techniques can also be used for to help classification and regression tasks. Okay, so here's one example. This is you take images of faces, you can sort of find a low-dimensional manifold of those faces and explore what they look like. Here's another example of unsupervised learning. It's pretty popular in the field of computational biology. Here's just one example. You typically have a big matrix. This is expression matrix of about 7,000 genes. These are rows and 64 columns, samples or people, for the human tumor data. And here you're looking at the heat map. Okay? So the questions you might ask are which samples are similar to other samples in terms of the expression levels across the genes. You're trying to basically figure out which people are similar to each other in terms of the expression levels. So effectively, we can think of it as clustering columns. Or you might also want to ask the question, which genes are similar to each other in terms of the expression levels across samples. And trying to find which genes are similar to each other. Okay? So these are traditional kinds of questions in unsupervised learning lab. So the plan for the course is that we're first going to focus on supervised learning, so that we have some background on supervised learning for regression and classification, and the rest of the course we're going to be focusing on unsupervised and semi-supervised learning. Okay? By the way, if you have any questions as I go through the talk, feel free to sort of ask me. So let's look at some.
All these slides are available online?
Yeah, the slides are going to be available online. You don't have to write them up. Everything is going to be available online, and I think the lectures is going to be recordings of the lectures as well, so you can, if you want to listen. Like sometimes I will go through some concepts very quickly, assuming that you have some background. Yeah. Okay, let's look at a very simple model. Linear least squares. This is something that you learn in your second year statistics course, I presume. But again, this is something that we need to cover because it forms the basis for a lot of models that we're going to be considering in this class. Right? And this is one of the most popular models that you can see being used everywhere, particularly in industry, just because it's simple, it's easy to fit and such. So the idea is the following. Suppose we have a vector of d-dimensional inputs, x1 up to xd, and we want to predict the target response using linear model. Very simple model. So here y is going to be given by just linear combination of the x's. Right? Now the term w sub naught is the intercept, and it's often called the bias term. Okay? So for us, it'd be often convenient to just include a constant variable 1 into x and just write it in this form. It's a truly linear model. Now, we're typically going to have a training set consisting of n observations, x1 up to xn, together with the corresponding target values, t1 up to tn. So x here is going to be n by d plus 1 matrix. D is dimensionality of the data, and 1 is for the bias term. Okay? So one thing that you can do is you can minimize the sum of the squares of the errors between the prediction, y, for each data point, and the corresponding real value target. So the loss function here is going to be sum of the squares, sum of square error function here. It's written here. Very straightforward, standard. And this is an example. You're basically trying to fit the lines so that the sum of squared of these green terms is as small as possible. Okay? You can also write it in terms of the matrix form this way. It's often going to be convenient for us to write it in the matrix form. Now, if X transpose X is non-singular, then the optimal solution, we have a closed form expression for the optimal solution. And again, if you haven't seen this, you probably should, because this is one of the most basic algorithms you can do anywhere, and that's the first algorithm you should apply to, because there's a closed form solution here. So W are the optimal parameters. X here, sometimes it's called design matrix. You have one input vector per row, and T is the vector of target values. Okay? So now, at an arbitrary point X, the prediction here is going to be taking a new point, X naught, and just multiplying it by double, by the optimal weights. Now, the entire model here is characterized by D+1 parameters, W star. Now, let's look at one example. Let's look at the example of polynomial curve fit. So here we have a training set containing n one-dimensional observations, so x1 up to xn, together with the corresponding real target values. So imagine that the blue circles is the training data set that you have. Okay? So let's look at how data set is generated. So the green plots here, the green is the true function, so it's sinus of 2 bar x. And the training set was generated by basically taking x, spacing them uniformly, and these blue circles, the target values, are computed by taking the corresponding values of the sine function and then adding a small Gaussian maze. So typically in practice, what's going to be happening is that you get to see the blue points, and you want to infer the green curve. You want to infer the true underlying function. Okay? So now our goal is to fit the data using polynomial function of this form. Okay, so let's look at this function. It's W0 plus W1x plus W2x squared, all the way up to the mth order. Okay. Now let's say you want to solve for the W's. Okay? How many of you think that there is a closed form solution for that problem? Can you solve exactly? Yeah. Great. Yes, you can. Any guesses why? So it kind of looks like we've just looked at the linear models, right? And that kind of doesn't look like a linear model. Right? So that's even though you can fit sort of a polynomial curve here. And that's a typical misconception that I see with a lot of people, because people think that linear models, you're sort of fitting only lines. When someone tells you, I'm going to be fitting a linear model, your immediate impression is that, well, you're going to be fitting lines. Right? But the key thing here is that this is a polynomial function. It's a nonlinear function of x, but it's a linear function of w. It's a linear function of parameters. And because it's a linear function of parameters, it's a linear model. You can solve for it exactly. So similarly, for the least squares, we can minimize the sum of the squares of the error between the predictions and the target. Right? Again, we can write it down this way, exactly the same as we've done it before. Similar to the least squares, you can minimize this, and there's an optimal solution, W0, W star here. The model here is characterized by n+1 parameters. Okay? Now, one key question, and again, this is a question that will be coming back throughout the course, is how do we choose m? How do we choose the degree of the polynomial? Okay? I show you this data. Should you choose 10-degree polynomial? Should you choose 100-degree polynomial? That's a key question that will be coming back to again and again through the course. So let's look at some fits to the data. So if we fit just 0-degree polynomial, we're just going to be fitting an intercept, a bias term, right? Obviously, that's not a very good fit to the data. if we feed a first-degree polynomial, then we'll be feeding the line. Right? It's probably not a good fit to the data either. If we feed a third-degree polynomial, this is how it looks like. And you know, it's not perfect, but it looks reasonable. Right? What if we fit 9-degree polynomial? Okay, the 9-degree polynomial looks like this. Right. Now, obviously, if you look at this, you might say, it doesn't look right. It's just, but for the 9-degree polynomial, we're fitting the data perfectly. Right? It's a perfect fit to the data. This function crosses all the blue circles. You know, perfect training fit. Right? And that's one of the key problems, is the problem of overfitting. So the overfitting, the idea here is that let's look at the separate test set. And the separate test set contains 100 new data points generated using the same procedure. Right? And now we're going to be looking at the test error, how well this model generalizes the new inputs. Okay? And this is what the training versus test error looks like as we increase the complexity of the model. Something interesting is happening here. Here, for the 9-degree polynomial, the training error is 0, but the test error is basically 1. She's basically not generalizing at all. Right? And the problem here is that the polynomial here, the 9-degree polynomial, contains 10 degrees of freedom, corresponding to the 10 parameters in your W. Right? So you can fit the data exactly to the 10 points. Okay? But the test error has become very large. Right? Why is this happening? Any guesses why this might be happening? You're fitting the data perfectly, but somehow the test doesn't generalize. Any guesses?
There's a lot of variation.
That's right. First of all, there's a lot of variation in the red curve. Right? But what really is happening here is that what's happening here is you're fitting noise as well as the true signal. Because this is a noisy targets, and when you're fitting a very complex model compared to the size of the data you have, you're going to be fitting noise. And that's exactly what's happening here. If you look at the coefficients here, the coefficients of the W, they become very large. So for the 9-degree polynomial, the coefficients have become fine-tuned to the data, and between the data points, there's huge oscillations in the function. And the idea here is, again, if you're building more flexible models, the larger degrees here, you're going to be tuning to the random noise on the targets. And that's known as an overfitting problem. You want to avoid that. Okay, so what happens with the size of the data? Okay. So here, if instead of 9 points, I have 15 points, then fitting 9-degree polynomial looks a little bit better. Right? If I have 100 points and I'm fitting 9-degree polynomial, it's actually a pretty good fit to the data. Right? So for a given model complexity, the overfitting becomes less severe, it essentially goes away as the size of the data set increases. So there's always a game that you're playing. You sort of, given the size of the data that you're fitting your function to compared to the complexity of the model, you have to balance the two. Okay? Now, the number of parameters, here I'm looking at the number of parameters as a measure of the complexity of the model. It's not the best way to measure the model complexity, but it's a pretty reasonable one for a lot of practical applications. Okay, but what we really want to do is we really want to achieve good generalization. Right? We really want to be making accurate predictions for unit test data points that we don't see during learning. Right? So a lot of what we're going to be talking in this course is how can we generalize to new inputs, make predictions on the new inputs. So one thing we can do is we can try to choose the parameters or fit the parameters that minimize the loss function on the training data. Right? That's the common thing that we do, but that might not be the best option. Right? Because we would like to model the true regularities in the data and ignore the noise in the data. And that often becomes a very hard problem. Right? It's often hard to know which regularities are real and which accidental due to particular training examples that you happen to pick. Right? That's a hard one. There's no good answer for how we can do that, other than just collect more data. Now, there's one intuition you should have in mind. We expect the model to generalize well if it explains the data well, given the complexity of the model. Okay? What does this mean? This basically means that if you have a lot of data and somehow your third-degree polynomial actually explains the data with 4 parameters, explains the data really well, then you're expecting it to generalize well as well. Right? If the model has as many degrees of freedom as the data, right, it can fit data perfectly, but that's not very informative. Right? I can always look, at the million-degree polynomial and perfectly fit the data. Right. So that's typical intuition that you should have in mind. Right? If you're looking at a simpler model and it happens to explain your data, fit data pretty well, then you're expecting that you can generalize better. Now, there is some theory, in particular coming from communities such as COLT, people working on learning theory. There's some theory on how to control complexity to optimize for generalization. We're not going to be covering that in this class, but again, for those who are interested, you can look at that later. Okay. So, what's a simple way to penalize the complexity? So, one technique for controlling overfitting is something that's called regularization, and you'll hear that term again and again. So, what it does is you're basically adding a penalty term to the error function. Looks like this. You're trying to solve for the squared sum of the squared error term plus a penalty. So this is sometimes called penalized error function. These are true targets. And this is a parameter called regularization parameter. Okay? And typically the norm here is defined as a provenience norm. Sometimes it's also called regularization term. And one thing to note is that we typically don't penalize the bias term, okay, just the offset. So let's look at what happens here if we're trying to solve for this penalized error function. If we actually look at the 9-degree polynomial and we set lambda, the log of lambda is -18. Yeah. This is how the fit looks like. This is a 9-degree polynomial. So you can see it sort of behaves much better. The idea here is that you shrink estimated parameters towards 0. Right? If you shrink them really, really heavily towards 0, then you're basically saying your model is going to be predicting 0 all the time. It's the simplest possible model. Predict 0. Get the C input, you predict 0. And shrinking to 0 here, you're penalizing coefficients based on the size. So you're basically saying I don't want to have coefficients that are very big, because that induces function that's very varies a lot. And this is known for the penalty function, which is the sum of the square of the parameters. This is known as a weight decay, or sometimes it's also known as ridge regression. And we'll come back to that term again. Okay. So what's happening with regularization here is if you don't regularize, almost a 0 regularization. This is the training error is 0, test error is 1. Right. As you increase the amount of regularization, notice what happens. The test error goes down, the training error goes up, and then at some point both of them go up. Right? So sometimes, here you are not penalizing, your model is complex enough. At this point here, you're penalizing it too heavily. Sort of becomes, it's now becoming, looking more like a linear function. Right? And again, for different types of regularizers, you have different the magnitude of the weight shrinks. So here it's almost close to zero. You're basically saying it's a function that's more or less very, very linear function. Now, we sort of come from one problem to another problem. Right? Looking at degree, the alpha degree polynomial versus how to choose this regularization coefficient. Right. So one very common way of choosing these parameters is something that's called cross-validation. Okay? So typically, if you have lots of data, you can divide the data set into 3 subsets. As a training data can be used for fitting learning parameters of the model. There's a validation data, which you're not going to be using for learning, but more for model selection. Selecting the regularization parameter, for example. And then there's a true test data. Test data is going to be used to get performance of the final model. Okay? So you're not supposed to play with the test data. Right. But for many applications, if your training and testing data is limited, right, it's kind of wasteful to, it's very hard to, first of all, set aside the validation set, because you can get very noisy estimates. And in particular, the validation set is small, and then you get noisy estimates of predicted performance. So sometimes it's fairly hard. So one way around it is, the technique that's commonly used is something that's called S-fold cross-validation. So often when you read machine learning papers, people will say, well, we use cross-validation. We use 5-fold cross-validation. Right? And the idea here is you essentially divide the data into S groups. Right? You're using S minus one of the groups for training the model, and then using the remaining one to do parameter tuning and get predictions. And then you essentially repeat this procedure S times. And then performance from the S runs is just averaged across all of these groups. Okay? So that way you're making use of all the data. Again, this is something that people are using if the data set is fairly small. In a lot of application domain, it is small. For the domains where you have lots of data, this is what people do. Okay, so let's look at probabilistic perspective on linear models. And again, that will help us build the framework for what we're going to be doing next. Okay. Now, suppose that our model actually comes from the following statistical model. The true targets are given by y here, which might be a linear model, plus some noise, where epsilon is a random error, and this random error has a Gaussian noise. And it's independent of x. That's very important. Okay. Then we're going to have the following statistical model. We're going to be saying that our targets have normal distribution. The mean of this distribution is given by our parametric function, y, could be a linear function. Think of this as x transpose w, plus some noise, beta. Right. So beta here is the precision parameter corresponding to the inverse variance. And the idea you should think about here is that if this is the data set that you see, the red one is the mean, and the beta is the precision parameter, effectively models the noise. Okay. Now, throughout this course, I'm going to be using probability distributions and probability density interchangeably. So typically when we're working with discrete random variables, we're going to be talking about probability distributions. When we're working with continuous random variables, we're going to be talking about density functions, but it should be obvious from the slides. Okay? So one very important thing in a lot of these statistical models are the basic assumptions. And these are key assumptions that we have to make in order to be able to learn anything. So let's make an assumption that the training examples are drawn independently from all possible examples, or from the same underlying distribution, the joint distribution P of x and t. Let's say there is true underlying distribution, which we don't know, but the samples that we get are independent samples. We also make an assumption that the training examples are identically distributed, or in other words, they are distributed according to the same underlying distribution. Okay? They're independent and they're identically distributed. Right? And one of the other key assumptions is that the test samples are going to be drawn exactly the same way from the same distribution as the training data. Actually, the training data. So it's not like, you're building your model on one data set, and then tomorrow the data set completely changed, the structure of the data completely changed, and then obviously you can't make any statements about, what your performance is going to be on this new test set. So this is IID assumption, and these assumptions, again, will make it unlikely that some strong regularities in training data will be absent in the test data. Okay? Now, this is one of the fundamental assumptions. It's a very strong assumption. There's a lot of work in the machine learning community where people are trying to get rid of those assumptions. So in one of the later classes, we're going to look at sequential models. And this is where assumption of independently is not true, because sequences, what's going to be happening a minute from now really depends on what's happening right now. And there's also a lot of work on domain adaptation. People try to figure out, well, what happens if your training set or your test set distribution really changes from the training set distribution? Right? How we can model that. But for us, let's just stick to these assumptions for now. Any questions so far? Okay. Now let's look at the maximum likelihood in this simple model. We're going to be making use of maximum likelihood a lot in this class. So if you haven't heard this term before, it would be good for you to read up on this. So if we assume that we're assuming an ID assumption, then we can write down the likelihood function. The likelihood function takes this form. Okay? So the probability of all the targets, because they're all independent, they're independently distributed, we basically can write them up as the product of these targets. Okay. Now, it's often going to be convenient for us to maximize the log of the likelihood function. So if we look at the log, it has this log. By making use of the equation for the normal distribution. And interestingly, what happens here is this term here, if you look at this term, it's just a scaled version of the sum of squares of error function, right? So maximizing log likelihood with respect to these parameters W under the assumption of a Gaussian noise. So we made an assumption that the noise has a Gaussian distribution. It's equivalent to minimizing the sum of squared error function. Right? Just kind of very nice relationship between the two. Right? So we can solve for this exactly. We can determine the maximum likelihood parameters by maximizing the log likelihood function. And then we can maximize with respect to the precision term. And it's effectively just looking at the value of the maximum likelihood estimation of the variance here. Okay? Now, if we make different assumption, different noise assumption, we say, no, the noise is not Gaussian, but it's Laplace, or if it has some other distribution, then this will not hold. Let's look at also the predictive distribution. So what is a predictive distribution? Well, what's the distribution of the targets given a new data point x, right? For a new value x? Well, it's going to have this distribution here. Right. It's effectively just a linear term here, and the maximum likelihood estimation of the noise. So in this case, if we fit the 9-degree polynomial here, I guess no, this is a 3-degree polynomial here, then the red curve is our maximum likelihood estimator, and these are the error bars, or the estimation of the variance. Now, obviously, you can see that it sort of doesn't estimate it quite correctly because of. But later on, we're going to look at the Bayesian linear regression model, and we'll show that you can actually fix this problem. Okay, let's let's spend another 15 minutes on statistical decision theory, and then we're going to take a little bit of break. So, statistical decision theory, I'm just going to give you a very brief introduction to statistical decision theory, and you can teach the course on that thing there. But this will be useful for us to just get some concepts, key concepts from here. So let's look at the small amount of theory that we'll need in order to look at a lot of models we're going to be considering next. Suppose we have a real value input x and a corresponding target t with some joint probability distribution. Okay? Our goal is to predict t given a new x. Right? Now, remember in regression, our output is going to be real value, continuous target. For classification, our output t here is going to be categorical variable, representing clusters. Okay? These are two common things. Now, the joint probability distribution here, the joint distribution of x and t, basically gives us a complete summary of uncertainties associated with these random variables. Okay. And determining this joint distribution from the training data, from a finite sample of the training data, is known as inference problem. Okay. So in general, what we'll get to see is some samples from this distribution and try to infer the underlying distribution. Okay, so let's look at an example. Let's take an example of medical diagnosis. Suppose let's look at the example. Suppose we have x, which is just a set of pixel densities. And we want to predict whether, based on these pixel densities, whether this image belongs to class 1, is cancer present, or belongs to class 2, cancer is absent. Okay? So our output is a categorical random variable, 0, 1. So we can choose t to be binary, 0 corresponds to class C1, and 1 corresponds to class C2. Now, inference problem here, we're going to be trying to determine the joint distribution over x and the class, or equivalent, we're going to be looking at the distribution P of xt. This is something that we can try to, if we assume some kind of form of this distribution, let's assume that it's a Gaussian distribution, or we can make more complex models here. However, in the end, we have to make a decision. So the decision typically comes, whether we want to give treatment to the patient or not. Right? So we can design fairly complex models that can explain the data well that we observe, but in the end, we have to make a decision. And that's where the decision theory comes in. Okay? So, the one thing we can do is we can compute conditional probabilities of the two classes. Okay? So this is known as a posterior probability of class K, given the data. And here, just basically using basic rules of probabilities, this is equality. This term is the probability of observed data given the class. This is sometimes called the prime probability of the class. And this whole equation is known as Bayesian. Okay. Now, we're going to look at the Bayesian framework next class. We're going to look at it very carefully next class. But this is one way of doing it. So obviously what you need to do here is you need to specify this model. What's the probability of observed data given a particular class? How your X-ray images should look like given there is cancer and given there is no cancer. There's some prior probability you have to define. And then you can infer the posterior probability. Okay? Now, if the goal is to minimize the probability of assigning X to the wrong class, then we should pick the class with the highest probability. Okay? We can compute this probability and you say, well, what's the highest posterior probability? And you pick that as your correct class. Okay? So let's look at what is happening here more precisely. So our goal is to make as few misclassification errors as possible, and we basically have to come up with a rule, right, to classify X into one of the existing classes. So let's look at this picture here. This is a probability distribution of class 1. Let's say these are healthy people. And this is the distribution of class 2. Let's say these are non-healthy people. obviously you can see there is overlap here. And X here represents some kind of, let's say, blood test. So what we need to do is we need to divide the space into regions. Sometimes these are called decision regions, such that points in each region are assigned to class CJ. So here's an example. Let's say this is our decision. We're basically saying all the, based on X, all of these X's are going to be assigned to class 1. All of these X's are going to be assigned to class 2. Okay? Let's say we've picked that decision boundary. Now, what's the probability of mistake? Right? Well, the probability of mistake is the sum of two terms. These are all the inputs that belong to class C2, but assigned to class 1. Right, so let's look at this. So if we say all of these guys here belong to class 1, well, all of these things, right, are going to be misclassified, right? Because these are healthy people. Well, these are not healthy people, sick people, being assigned as healthy people, right? And the blue region here, again, inputs that belong to class C1, an input that belongs to class C1 but is assigned to C2. Obviously, we're making this classification errors here. And you can write them in terms of just integrating over the relevant parts of this. So you basically look at the volumes here. Okay? Now, one question for you is this a good classification decision? Can you decrease the probability of making mistakes?
Yes.
Yes. This decision rule, you are going to be making fewer mistakes. Right? The reason why is because now let's look at the mistakes that you're going to be making. The mistakes you're going to be making are these guys. But you're not going to be making mistakes with these guys. So what's happening here is if the joint probability X in C1 is greater than the joint probability of X in C2, then you're assigning X to class 1. Otherwise, you're assigning X to class 2. The other way to think about this problem here is to minimize the probability of making a mistake. You're going to be assigning each X to the class for which the posterior probability is the largest. So obviously here, notice that's the point where the posterior probability for class 1 is the largest, and here the posterior probability for class 2 is the largest. So that's pretty straightforward. But then comes the notion of expected loss, or the loss function. So far we haven't really looked at the loss function. So loss function here, we want to have an overall measure of the loss which is incurred by taking any of the available decisions. So suppose that for X, the true class is C sub K, but we assign X to class J. Okay? So we're making a mistake. Then we're going to be incurring a loss, LKJ, and sometimes called the loss matrix. So let's look at an example. Here's an example of loss matrix for our case. Let's say that the truth is, it's a cancer patient. The decision is a cancer. You're incurring a loss of 0. If the truth is normal, and the decision is normal, you incur a cost of 0. Let's say the truth is normal, and your model predicts that cancer, then you're incurring some loss. Right? It's always annoying, you go to the doctor and says, well, you have to run more tests. Right? That's annoying. But if the truth is cancer and your model predicts normal, you're suffering a lot of loss. That's pretty bad. Right? You go to the doctor, you have cancer, the doctor says, no, you're fine. That's pretty bad. Because you might actually die. So there is a huge loss here. And now what you want to do is you want to include this information into your model so you can find the right decision boundaries. Right? And again, the notion of expected loss, you're effectively weighting the probabilities by the corresponding loss terms. So here's one example. If you go back to this example here, let's say, again, these are healthy people, and these are cancer patients. Where would you place your decision boundary based on the loss matrix that I've shown you? Would you move decision boundary to the right, or would you move decision boundary to the left? Any guesses? Left? Don't be shy. Yes, you move the decision boundary to the left, right? If you move decision boundary to the left here, what's going to be happening is you're going to be catching only people who have cancer. But at the same time, there's going to be a lot of people who don't have cancer, and you're going to be incurring a little bit of loss. So you're going to have a lot of happy patients, but at the same time, again, that would be the decision boundary. So depending on your loss, your decision boundaries can change. And that's very important. How, questions come into play in practice. How do you define loss? What is the correct loss? How many people you want to upset versus how many people you want to catch and such. Well, it depends on this. Okay, there is also something that's called reject option. It's commonly used in practice where you're basically saying that all x's up to this point are going to be belonging to class 1 because the posterior is high enough. All the x's up to here are going to be belonging to class 2, posterior distribution for class 2, and this is a reject region. This is where you say, your model basically says, I don't know. That's a commonly used thing. Somebody in the loop, like a human or a doctor, can look at those cases more carefully. Okay? It's typically something that's being used in practice a lot. Okay, before we get into the regression, let's take a 10-minute break. So let's come back at 12:20.
You see this course is there any chance we stand
that what two people is that this on the line is more it's the more accurate. Talking about the mixture is the conditions, the marginal bits.
Yes, that's right.
And then when we go to process, it becomes the one executed
This is typically, so this is the case of super large. Enforcement money when you're
Can we find a given shot? First of all, thank you.
列力山。
Simon, one individual. Individual project something new.
这个确实是 individual project， 这太吓人了 ，original idea。
Yes, just listening. I should be able to work with
always miss the signal.
我觉得我唱片很大，但是我对可能结果很低。
那会儿微碟看了。
但是那个 CSL 是不是很有用？我还不能理解这个 video。
放在这儿，谁可以为什么讲？对，你看我的前面，看这个第二部，
Okay, why don't we keep going? So we've started looking at a little bit of decision theory, right? So let's look at what's happening in the regression case. Okay. So in the regression case, x is again going to be a real valued input vector. T here is going to be denoting a real valued random target, the output, and we have a joint probability distribution. Here again, we make an assumption that there is underlying joint probability distribution. The decision step here is going to be finding an estimate, y of x, of t for each input x. Okay? So this is the function that we want to estimate based on the training data. Right? So again, just remember our example is that the blue surface is something that we observe, and we would like to fit some kind of function y of x. And this is our fit to that function. Now, similar to classification case, we also want to quantify what it means for us to do well with this task. And we have to define loss function, or sometimes people also call it error function. Now, the average or expected loss is going to be given by this expression. So a lot of times you'll hear terms like what's expected loss? Well, it's basically the loss average over over x and t, over distribution of x and t. Now, if we use squared loss, then this is expected, the definition of expected loss. Now, these terms here are just theoretical constructs, because in practice you can never compute this expectation, right? You can never compute these expectations because you don't know what the true joint probability is. You can try to estimate what the probability distribution is and then estimate the expected loss. But let's look at the squared loss. This is the most commonly used loss function for regression. Right? Now, the goal here is to choose function y so as to minimize the expected squared loss. It turns out that the optimal solution, if we just were free to choose completely flexible function, right? The optimal solution is going to be the conditional average, or the conditional expectation. So the true solution here is going to be given by the conditional expectation of targets given x. Again, this expectation is taken with respect to the true conditional probability. Okay? So when you look at the squared loss, and you're using regression, then the optimal solution is going to be given by conditional expectation. And again, the way to think about this, if this is your true function, there is some noise, your optimal value is going to be given by the conditional expectation. So the regression function x that minimizes this squared loss is given by the mean of the conditional solution. Now let's look at why this is the case. Let's prove this. So here's one trick to prove this this particular fact. So what we're going to do, let's look at the squared term here, yx minus t. So yx is our model, t is the true targets. And what we're going to do is we're going to subtract and add these conditional expectations. Now, if we open the squares, we're going to have, obviously, we're going to have three terms. The first term here corresponds to the first two terms here. The last term here corresponds to the square of this term, and then there is a cross product. Okay? It's a very simple algebra. Now, if we plug this into the expected loss, or if we take an expectation of this thing here, the expectation will have this form. Okay? Notice that this term here doesn't depend on t, so this term doesn't depend on t, because it's expectation. So p of x dx. This term here is the definition of the variance. So it's variance of the condition on t, and then the average of p of x. Now, this term here disappears. Any guesses why it disappears? Why when we take an expectation with respect to the joints? That's right. The second one goes to 0. Take an expectation here. Right? Here's expectation t given x minus expectation. You can also write it as expectation of t given x. That is the margin of p of x. This term is going to be 0. So now, basically, the expected loss is given by these two expressions. And I think in one of the homeworks you'll play with, for people who are taking the class, one of your homeworks you will play with these derivations. So you'll practice it a little bit. But now, if we look at this term is minimized when your function is given by the conditional expectation. In fact, this term is going to be 0 when your function is given by the conditional expectation. Right? This term here represents the intrinsic variability of the target values. It represents, because it's independent noise, it represents an irreducible minimum value of expected loss. Right? So this is how your targets vary conditional on x, something that you cannot reduce. So the intuition here you should think about it is it's some form of a measurement noise. Right? You can only measure, let's say you're trying to measure some value. You can only measure that value up to the 10th decimal point. Right? And that is being represented here. You cannot go beyond the noise in the targets. Right? Any questions? Right. Now, in terms of other losses, there are simple generalizations of the squared loss. These are called Minkowski's loss, where instead of having a square, you raise it to the q power. Okay? Now, the interesting thing is that when q equals to 2, the optimum is going to be given by the conditional mean. When q equals to 1, the optimum is going to be given by conditional median. When q equals, or is approaching 0, the optimal is going to be given by the conditional mode, right? The most probable, the mode of the distribution. Okay. So depending on what kind of loss function you choose, you'll get different values of y, different functions that you fit in. Okay, so now, one of the things I should point out is that when we're looking at, in particular when we're looking at supervised learning techniques, right, such as regression, classification, there are two different ways of thinking about these models. And you hear a lot of these things when you go to machine learning conferences. And these are known as discriminative versus generative approaches. Okay? Now, the idea of generative approach is that you want to model the joint density, the joint probability distribution of x and t. Okay? So here you might want to have the conditional p of x dot t times p of x. Or you want to model the joint distribution of inputs and pluses. Okay? And now what we can do, once we have the joint, we can infer the conditional. Right? We can compute the conditional distribution of the targets given the data. And we can just use Bayesian to do that. Okay? So this is known as a generative approach. The reason why it's called generative because we have to specify the probability of x given the targets or given the classes. So this is sometimes called the generative approach because you have to specify what's the distribution of an input given a particular class. Right? Now the discriminative approach takes a slightly different form. Here you're trying to model the conditional density of targets given the x. And you're trying to model it directly. Okay? Now what's the difference between these two? There was an interesting example that happened, I think, in the late 80s, early 90s, where here's the problem that was considered. Let's say you're trying to detect tanks. I show you an image, and you're trying to say, is there a tank in the image or not? Okay? Very useful thing to have, I guess. People were interested in doing that stuff. So now you're fitting this model, the discriminative model, right? Based on the pixel values, you're trying to predict there's a tank or not. And the data set was collected and such, and then basically people got perfect test errors. You can perfectly classify whether there is a tank or no tank in the image. Okay? So it was exciting until people realized what was happening when we were fitting this model. So what was happening is pictures with tanks were taken on gloomy day, and pictures without tanks were taken on a sunny day. Okay? So what the system was doing, the system was just basically looking at the clouds, looking at the average pixels of the clouds and say, well, if it's darker, then there is a tank. If it's brighter, there is no tank. Right? Completely ignoring what was going on in the rest of the image. Right? And this is roughly what the discriminative approaches are doing. You can think of discriminative approaches as basically trying to figure out, you're not trying to model how tanks look like. You're basically trying to extract some features from the image in order to classify it. Now, this approach would have been different because here you actually have to specify what's the distribution of all pixel values, given there is a tank and given there is no tank. So these two approaches are very competitive with each other. The drawback of the generative approach is that it's sometimes very hard to specify. You know, like building a generative model of tanks is really hard, right? Because different viewpoints, different variations, different lighting conditions, and such, and then everything in here has to go in here. So again, you know, if you look at the machine learning communities, these are two separate approaches. Sometimes people working in the domain of semi-supervised learning or unsupervised learning tend to work in the generative model domain, because here, if you actually don't have targets, you can still, you know, iterate out the targets, so you can still incorporate that information into these models. These models typically, if you have input X but no target T, typically it's not very useful for these models. So it's much harder to incorporate unlabeled data into the discriminative models. But in a lot of practical applications, these discriminative models are actually working really, really well. So speech recognition, vision domains, and such. Okay, now let's look at another class of functions. These are called linear basis functions. Remember we looked at the simplest linear model for regression, where X here was a d-dimensional input vector, or sometimes these are also called covariates. Now the key property of this form was that the function was linear in terms of parameters, right? In the parameter space, the function was linear function of the parameters. However, it doesn't have to be a linear function of the input variables. Okay? So a very common thing that people do in practice is to consider a different type of a function where you're basically having these phi j's, and these are called basis functions. Okay? So you can think of these basis functions as some nonlinear functions of x that we have to specify. Now, typically, phi 0x is 1, so that w0x is a bias term, or intercept again. In the simplest case, if you use linear basis functions, then you're basically saying the jth function of x is just the jth component of x. And that would reduce it back to the linear function. Okay? So, but using non-linear basis functions allows our decision function, or our y, to be non-linear function of the input space. And that sometimes can be very, very useful. Let's look at some commonly used basis functions. These are polynomial basis functions, right? Taking x to the power of j. This is exactly what we were looking at when we were fitting polynomial curves. These basis functions are global, meaning that small changes in x affect all basis functions. Okay? These are Gaussian basis functions. These are very commonly used in practice. You basically have functions of this form. These basis functions are local. Small changes in x affect only nearby basis functions. And these means and these s's control the location and scale the width of the basis functions. Something that you have to specify. There's also sigmoidal basis functions. This is known as the sigmoid activation function. Yeah, they also look like this, somewhat different. They're also local, small changes in x. So if you change x, it will affect only nearby basis functions, not the far away basis functions. And again, s and mu control the mean and scale. So why is this useful? And again, as I mentioned before, decision boundaries will be linear in this feature space, fine, but they would correspond nonlinear boundaries in the original space X. Now, one question is how do you come up with these basis functions? That's something that you have to design yourself. So, and again, classes that are linearly separable in the feature space need not be linearly separable in the original space. Here's one example of this. Let's say you have three classes, so two classes, okay? You try to build a classifier. Try to separate one class from another class. Now, obviously, in this case, these classes are not linearly separable, right? So what I can do is I can define two basis functions, phi1 and phi2, these Gaussian basis functions. And if I transform the data using these basis functions, in the basis function space, phi 1 and phi 2, these points become linearly separable. Okay. And notice that the decision boundary in this space corresponds to a decision boundary in this space, which is this decision boundary. So, so here the decision boundary, right, is just using we're just using logistic regression here, and again it corresponds to no linear decision boundary in the weighted space. Now we'll come back to the basis functions later in the course again, but again this is just to keep in mind that trying to figure out what the right space to work in is very important. Okay? And more recently, people actually started looking at models that allow you to learn what these basis functions or what these nonlinear transformations should be. And that's part of the sort of the deep learning trend where people are trying to figure out what are the right representations and what the right features to use so that you are in that space and not in that space. So how do you transform from that space into that space? Okay, let's look at the maximum likelihood as before. This is just the repetition of what we had before. As before, remember our targets. We're going to have a linear model, a linear Gaussian model. The noise here has a Gaussian distribution. Given a set of observed inputs, we can write down the likelihood function. And again, the only change that's happening from the previous slides is that here x is now 5x. Some nonlinear transformation of x. Using Gaussian basis functions, sigmoidal basis functions. Right? Phi here is an n-dimensional vector, so here we're using n basis functions. Okay. Now, if we look at the log of the likelihood function, we have this form, and again, sum of squared error functions is exactly the same as we had before. No big changes here. Differentiating it, if you differentiate the log likelihood function with respect to I guess minus w, you have this one here. And again, this is a linear model because it's linear in w. If you're differentiating it, solving for w, you get this one. Phi, again, is known as a design matrix. It's a matrix which is of size n by m. N is the number of data points, m is the number of basis functions. And this is known as a pseudo-inverse. Again. Just as before, remember before when we were looking at simple least squared estimator, this was just x transpose x inverse x transpose t. Well, now we're just replacing x with phi. Right, so you're working in a feature space, in some basis space, but nothing has changed. There's just the key idea I want to communicate here is that, again, when you look at linear models, don't think of linear models as just fitting lines. Because you can design features that are non-linear functions of x, as long as the model is linear in the parameters. Now let's look at the geometry of least squares. This is a very important concept, just the intuition for you to have. Let's look at the n-dimensional space. So the targets here is a vector in that space. So let's look at the targets. These targets lie in n-dimensional space because there are n of them. Okay? Now each basis function, phi, is evaluated at the n data points, and it can be represented as a vector in the same space, right? Because you can evaluate it at each one of the n points. Now, if m, the number of basis functions, is less than n, the number of data points, then the m basis functions will span a linear subspace S, which will have dimensionality n, okay? Because these are m-dimensional basis functions. So think of this as a subspace here where these phi vectors are. Right? So in this case, one of these vectors corresponds to this vector here. Now we're going to define y as the matrix phi times the maximum likelihood estimate. That's effectively our predictions. And it turns out now this y will lie in the subspace S. Right? And the idea behind the least squares is it is basically saying the solution here just corresponds to a orthogonal projection of T onto the subspace S. So you're taking t and projecting it to the subspace. That's going to be the optimal solution done. Because anywhere y, if you pick any other y, the distance from this line to the target is going to be bigger. Right? So that's the idea behind, roughly the idea behind the least square estimator. You're taking a vector t and you're projecting it down to the s-dimensional subspace. Now, there is another key component to learning these models, sometimes called online learning or sequential learning. And the idea here is that if the training examples are presented one at a time, sequentially, the parameters of the model can be updated after each observed example, or each time you're being presented with an example. So in this case, E sub m is just an error function, but it's vector of derivatives of the square error with respect to the parameters, or a particular training case that's presented at time t. This is known as a learning rate, a scale, and this is the updates of the parameters and the weights after seeing the t plus 1 example. Right? In case of sum of square error function, this is the expression here. It's just a derivative. You take a derivative, you take a step in the direction opposite to the derivative. Obviously, the maximum likelihood direction of derivative. This is known as a stochastic gradient descent. So the training examples here are picked at random. And in this case, this is a fairly dominant technique when you're dealing with very large data sets. Now you have to be careful in terms of choosing the learning rates to ensure that the algorithm converges. There's a lot of theory on how to choose the right learning rates and different variations of these algorithms and such. But the idea you should keep in mind here is that for these puzzle models, for these linear models, you can actually do online learning. Given one example, you update the parameter. Given another example, you update the parameter. And that's a dominant technique. If you have billions of data points and you want to fit a model, then you can do it in sequential. The key assumption here is that the training examples are picked at random. Right? And the intuition here is that because they're picked at random, you basically get noisy estimates of the true gradient that you would average over the entire data set. But the expected value of that gradient is the correct value. Right? On expectation, you're doing the right thing. On average, you're doing the right thing. So that's a dominant technique. We'll talk a little bit about stochastic gradient descent as we consider some of the other models. Okay, now regularization. We've talked a little bit about regularization, but let's us consider the following error function. Again, we have a data term and we have a regularization term. Lambda again is called regularization coefficient. Remember, we've looked at penalized least squared estimator here. You have quadratic term plus the penalty here. Remarkably, for this particular objective function, it's minimized, has a global solution, and this is known as a ridge regression. Okay. So what's happening here is that for the optimal solution, you effectively add a positive constant to the diagonal of this matrix. Okay? What it does is that it makes this matrix non-singular, even if phi transpose phi is singular. So in particular, this might happen when the number of training examples is less than the number of basis functions. Or in the cases where you have lots of dimensions in your data, but very few samples. Typically, computational biology is one example where this is happening a lot. Now, what's happening here, the effect of regularization, is as follows. Right? This is your penalty function, the quadratic model, and let's say this is your error function. Right? If you don't penalize, this would be the optimum. If you penalize, the optimum is going to be lying on some line connecting the zero and the connecting the zero and the optimum. So you're basically taking the optimum and shrinking it back to zero. That's the intuition you should have. Now, there are other kinds of regularizers. In particular, one extension is you can look at the sum of the weights raised to the power of q. And it turns out, there are different regularizers. For q equals to 2, it's just a quadratic penalty. For q equals to 1, this is known as lasso. You've probably heard about lasso. I mean, if you ever dealt with sort of sparse data and such, which is very heavily used technique. If you have q equals to 0.5, you sort of have these kinds of penalty terms. But one of the dominant technique that's been very successful is the lasso. The idea, again, you're trying to solve for a W where your penalty, you look at the sum of the absolute values. And it's remarkable, this technique was developed by Rob Tibshirani, who was a prof here at Toronto and then moved to Stanford. It's a remarkable technique being used almost everywhere in all different fields. Yes, this paper has like 30 or 40,000 citations. It's like pretty remarkable, right? And I always joke that all you have to do is you replace square by 1 here. But what is happening here is that for sufficiently large lambda, some of the coefficients here are going to be driven to exactly 0, leaving us with a sparse model. So you're basically shutting off some of the w's. You're driving some of the w's to zeros. So what you get is you get sparse solution. The above formulation is also equivalent to this formulation, where if you're looking at the sum of the squared error term, it's subject to this constraint. You look at the sum of the absolute values, they should be less than some value tau. Right? So this is unregularized but subject to this constraint, and the two approaches are actually equivalent. They related to each other using something that's called Lagrange multipliers. This is formulation is probably more often you see in practice. But one of the beauty of lasso is that there is a solution. It's a unique solution. It's a convex optimization problem. The solution is given by something that's called quadratic programming problem, and that can be solved efficiently. That's what made this model so popular. The solution to convex optimization problem is a global solution. You can solve for it efficiently using various techniques. So if you're dealing in situations, particular situations where the dimensionality of the data is very large compared to the number of samples, these types of models are the dominant models. If you look at the space of medical imaging, it's a very dominant technique used there. So why does it give us sparse solutions? The idea is here, this is L1 regularizer. And this is the quadratic penalty. This is the quadratic error function that we optimize. If you look at where the blue curve is likely to touch the penalty term some of the corners, at the corners of this value. So that's why often you get very sparse solution with lasso. Now, finally, let's look at the last component that I'm going to do in this lecture. It's a fairly important one, is the bias variance decomposition. Again, that sort of will help us understand a little bit the relationship between the bias and the variance and the notion of model complexity and overfitting. So obviously you've seen even for lasso, you put in the L1 regularization, sometimes these called L1 regularizers, precisely because you're basically saying some of the coefficients should be 0. You want to restrict the complexity of the model. So let's look at the expected squared loss function. And remember, the expected squared loss function had two terms. Right? And again, the optimal prediction is given by the conditional expectation. Right? So roughly speaking, the optimal H is given by the conditional expectation, something that we don't know. We can't compute exactly because we don't know the true conditional probability. And this here represents the intrinsic variability of the target values. This is something that we cannot control. So now, if we model h of x, if we model this conditional expectation using some kind of parametric function, just like we're doing it right now, then there are two different ways of thinking about this model. Where does the uncertainty come from? Well, from a Bayesian perspective, again, something that we're going to be covering in the next class, the uncertainty is going to be expressed through something that's called posterior distribution of the parameters. Okay? And it's a very intuitive notion of uncertainty, but in the remaining lecture today, we're going to be looking at frequencies perspective. So I should also point out that there are two dominant techniques or perspectives in statistics communities. There's a frequencies perspective, there's a Bayesian perspective. How many of you have heard about the differences between the two, or heard about maybe somewhat? So there's sort of two dominant techniques, and people who do frequency statistics don't do Bayesian statistics, and people who do Bayesian statistics typically don't do the frequency statistics. It's sort of a mindset of two different ways of thinking about statistics. So we're going to look at the frequency statistics, and in the next lecture we're going to look at the Bayesian versions of these models. I guess one thing I should point out is just the intuition to have for you, in particular people who are not in the statistics, don't come from the statistics communities, is the difference really comes in terms of thinking about uncertainties. How do you measure uncertainty in your parameter estimates, for example? Okay. Frequentists typically think of uncertainties in terms of repeated experiments. Right? So you have an estimator. If you repeat this procedure, you have some procedure to get an estimate of your parameters. If you repeat this procedure multiple times on different data sets, that will measure the uncertainty. Right? From the Bayesian perspective, the uncertainty is being measured in terms of the prior probability over the parameters or the quantities that you're trying to estimate. The prior probability should come from the background knowledge. And I hear frequencies sometimes say, yeah, but you don't know where Bayesians have to design these priors, where does the priors come from? But at the same time, Bayesians say, well, you get to observe one data set. How can you do this repeated experiment multiple times? It's a little bit tricky. And it's also philosophically a little bit, the two approaches are somewhat different. But let's look at the frequencies perspective first. Okay. So from the frequencies perspective, we make a point estimate of W star based on the data set D. Okay. So here's the data set. We fit our 9-degree polynomial. Now we next interpret the uncertainty of this estimate through the following thought experiment. Okay. Suppose we had a large number of data sets, each of size n, where each data set is drawn independently from the underlying distribution. Okay? Now, you may say, well, in practice, I might not have, you're trying to fit something, given a data, you're trying to fit your model, and now you're basically saying, suppose I actually had many of these data sets. It's something that we don't really have in practice, but this is more of a thought experiment. Suppose we had a large number of these data sets. For each data set, we can obtain a prediction function y. We can fit our model to all of these data sets. Now, different data sets will give rise to different prediction functions. Right? Because these are finite data sets. Obviously, every time you fit the same model to a different data set, it might look different. Right? And then the performance of a particular one of the algorithm is then measured by taking the average of all of these data sets. Okay? So now, let's look at this expression. Let's look at the expression of our model, fit on data set D, compared to the truth. Think of h of x as the conditional expectation. Okay? Now, this quantity depends on a particular data set D. So now, what we can do is we can add and subtract the term to this term, which is the expectation taken with respect to the data set D. So it's just average for all different data sets. We're averaging your predictions over all different data sets. So now let's look at this expression. We add and subtract these expectations. We use the trick that we've used before. You squaring it, and you open the parentheses. So this corresponds to the first term, this corresponds to this term, and then there's a cross product between the terms. Now, if I take an expectation over d, this last term there vanishes. The reason why it vanishes is if I take an expectation with respect to d here, this expectation with respect to d, and then with respect to d, this term becomes 0. So now, just like as before, we have two terms here. And these terms have specific meaning. This is known as a bias, squared, and this is known as a variance. Okay. Now, from the formulas, it might be a little bit hard to see what is exactly going on here. So let's look at these terms a little bit more precisely. So when we look at expected loss, the expected loss is decomposed into the bias squared plus variance plus noise. Okay. Now let's look at the bias. What is the bias here? That's the definition of the bias. This measures, if we take an average of all the data sets, this measures how the average predictions differ from the optimal regression function. Okay? So if I average my predictions over this big ensemble, how close it is to the truth. Okay? That's known as bias. The second term is the variance, and let's look at the variance. The variance here is somehow solutions to individual data sets, this is for a particular data set, vary around their averages. Right? That's the definition of the variance. You know, you fit your model to a particular data set, how much it's different from the one where you're averaging over all data sets. Does it vary a lot? Does it vary not a lot? So it's basically telling you how sensitive your model to a particular data set. Right? So think of 9-degree polynomial. Right? Remember, it was like a very wiggly function. Well, if I give you 9 other points, right, then your function is going to change a lot. If I give you 9 other points, your functions are going to change a lot. So it's going to have a huge variance, because when you average over all of these functions, the solutions to individual functions will be very different from the average. And then there is a noise here. So this is intrinsic variability of the target noise. We can't really do much about this. So what's the difference? There's a trade-off between bias and variance. On one hand, you want to have flexible functions. You want to bring the bias down. Because you want to have a flexible function such that when you average your whole data set, it approaches the true function, no matter how complex the true function is. So with very flexible model, or high complexity model, we have low bias, but we'll have high variance. Think of, if I told you I'm going to fit a 1 billion-degree polynomial. That's a very flexible model. You can fit a lot of data using a 1 billion-degree polynomial. Right? And if you had 1 trillion data points, that would be a very good model to fit. Right? So you want to have flexible model because you want to have low bias, but unfortunately the variance is high. With relatively rigid models, or models that have low complexity, think about fitting lines or 3rd-degree polynomials, you're going to have high bias, but you're going to have low variance. In fact, if you're fitting the model that basically predicts 0 all the time, you will have no variance at all. No matter what data set you look at, you're going to be predicting 0, so variance is going to be 0. Right? So you can drive this term to be 0, but the bias is going to be very high. So there's always a trade-off between these two quantities for a given data set. So the model with optimal predictive capabilities is going to have to balance between the bias and variance. Here are some examples just to illustrate what is happening here. So let's look at the previous data set, the sign data set. We generate 100 data sets, each containing 25 points, and then we draw independently from the sign 2 pi of x. So just 25 points, we draw 25 points from the sign function. Now, if we take our regularization coefficient here and make it fairly small, and this is, I guess, we're picking 9-degree polynomial, look what happens. So each curve here is a fit to a particular data set. Okay. So you can see there is a lot of variance, right? Because for any particular data set you observe, your function might go like this. Right? So there's a lot of variance. But if we average over all of these 100 different data sets, the prediction is pretty good. So it has small bias. Basically means that the model is pretty powerful. Okay? Now, if we increase the regularization, the variance goes down, so it's less wiggly, like you can see here, but the bias increases. Okay? Now, if we make regularization very, very high, we're basically penalizing our model, extremely penalizing our model. And look, the variance is very small. Different data sets, you basically fit a similar function. There is no variability, much variability between the functions. So you can think that these models are somewhat a little bit robust. No matter what kind of data set you see, you're fitting something that doesn't vary a lot from data set to data set. So what's happening here, there's a lot of variability from data set to data set. Here, there's almost real variability from data set to data set. But the problem is the bias. It has high bias. Right? And so there's always a trade-off between, and the regularization coefficient effectively, in our case, is controlling for the model complexity. So I have to choose the right complexity of the model. So here's what's happening with the trade-off. So let's look at this graph here. So this is the test error. Notice that it goes down and then it goes up. This is the bias. This is the variance. And the magenta curve is bias plus variance. Okay? So a couple of things to notice here. If you don't, this is long. So what's happening here? The large values of W for all the regularized models, so all the regularized models as you can here, bias goes up, the variance goes down. For under-regularized models, bias goes to 0, but variance goes up. And the optimal is somewhere in between, so I guess it's somewhere over here. There's an optimal trade between bias and the variance for a particular data set you're looking at. Okay? Any questions? So that's a key concept in machine learning. Sometimes you hear people talking about what's the bias variance trade-off. You want to build flexible models, but again, if the model is too flexible for a given data set, your performance might not be as good. So how can we beat bias and variance? And there's a number of techniques that we developed in order to try to basically maybe reduce the variance of the estimators. So one way to reduce the variance is by training, is by averaging over many models that are trained on different data sets. That's always good. You have many different data sets. Averaging over these data sets is always a good thing. Okay? More data, if you have more data, it can't hurt you. So in practice, unfortunately, you typically have a single data set. It's not like you come in to physicians and he says, here's 5,000 different data sets I have, right? Of the same thing that I'm trying to model. In fact, if we had many independent training sets, we'd be just better off combining them together into one big data set. It's always the case. With more data, we have less variance. It's always the case that with more data, we'll have less variance. If you're trying to fit some form of a model with more data, you can reduce the variance of the estimate. So it can't hurt you. Now, given a standard data set D of size n, we could in principle generate new training sets n by sampling examples from our data set D uniformly and with replacement. So this is a technique known as bagging. And it actually works quite well in practice. Right? So again, what is happening here, all you're basically doing is that for a given data set, you just keep creating new data set by sampling from this data set with replacement. So sometimes entries will repeat, sometimes entries will not repeat, and that's a way to somehow try to create multiple data sets. With enough computations, however, we would be better off by using Bayesian framework. So there is sort of a different type of approach to dealing with that problem. And in the Bayesian approach, we're going to be combining predictions of many models using the posterior probability of each parameter as the combination weight. It's another technique. Now, one of the drawbacks of Bayesian frameworks is that occasionally it's computationally intensive. So that becomes a major bottleneck for these models, for the Bayesian models. Something that we're going to look at the next class. But in practice, bagging is actually working fairly well. Okay, so let me stop here. In the next class, we're going to be looking, again, as I mentioned before, in the next class, we're going to be looking at Bayesian framework, and we're going to be looking at ways of computing posterior probabilities. Okay? So that's going to be the topic for the next class. Any questions? One question are the office hours. So I haven't figured out exactly when the office hours and such, but I'll probably let you know next class when I'm going to have office hours. Especially for students who are taking this course for credit, that would be very valuable.
After Monday, option after this class.
Oh yeah, so initially I was thinking of setting up to be on Monday after this class. Does that work for everybody?
Yes.
Okay. Good. So we're going to make office hours after the class. Now, generally, we're not going to be using all 3 hours for the class lecture, so it's generally going to be 2.5 hours. So we can have office hours after the class. Probably more convenient for everybody.
Great.
Okay.